Hi, everyone. Welcome to Talk Math with your friends. It's my pleasure today to present our speaker, um, Brian Lee, a student from the University of Toronto, who's going to be telling us about uh, magic tricks involving set. So please join me in welcoming Brian.
All right. Can everyone hear me and see my screen?
Yes.
Okay. Awesome. Okay. So, let me just open the chat because I know BK's operate kind of like looking at the chat, but I just want to make sure like I get updates on everything. Okay. Awesome. Let's get started. Whew. Okay. So my name is Brian, and I'm currently undergraduate at the University of Toronto. And today my talk will be about a magic trick using the set deck. For those that's not very familiar with what set is, I will be introducing that later. It is actually a very fun game. I think it's especially popular within mathematicians. All right, so quick introduction. Like I said, I'm an undergrad. I enjoy exploring new mathematical card tricks. And this work is actually a collaboration with Professor Parker Glenn, who is an assistant professor of mathematics at the University of Toronto, Mississauga. He works in math education, combinatorics, and geometries. I was lucky to land an independent study course with him past summer, so it's very nice of him. Okay, so today's content. First of all, I want to introduce a bit about the inspiration, like why we're doing this, where does it come from? And then I will give a quick introduction of what set is, since it's kind of relevant to the trick itself. And we'll do a quick demonstration of the trick. It will not be like in person, unfortunately, but I will try my best to make it impressive. And then I'll talk about what's behind the trick. We have to introduce something called a deburring sequence, the deburring graphs, and then we will talk about how this trick actually works and what's the math behind it. All right, so the talk itself should be around 30 to 40 minutes because this is about magic tricks, so I want to leave more time for discussion, or if anyone has a cool idea for magic trick, we could share that as well. All right. So the inspiration of the trick that we named in TetraCycles is actually another trick named in cycles. So this trick was being outlined in this book called Magical Mathematics. I actually have a hard copy here, thanks to my girlfriend. It is written by Persi, Diaconis, and Ronald Graham. The entire book is about, oh, you have the book? That's awesome. Yes, it's a really good book. It outlines a lot of interesting mathematics behind the trick. And so this trick in particular is in chapter 3, if you have the book. It is a trick called in cycles, and I will give a quick overview of what this trick is. So the way that the writer described the trick on the book is actually a lot more impressive than this, because magic trick tends to have a lot of distractions to make the volunteers confused, I guess. But in order to fit it into the slides, I put a summarized version of it. So what happened is that the performer has a deck of cards, which he or she has cut multiple times in front of the audience. Yeah, I think BK just attached the link. Thank you for that. And then 5 volunteers were randomly chosen, and they are asked to take the top cards, then pass on to another volunteer. So what happened is that, let's say if you have a deck of cards, the magician will kind of just cut it. So by cutting, we don't mean by shuffle. So cutting basically means that you remove a part of the top, and then you put it at the bottom. And basically, this is the motion. And then the card was being handed out to the volunteers. So let's say I'm the first volunteer. I will take the top cards. I will put it down, and then I will pass the entire deck to the other volunteers. And then the other volunteer will do the same thing until we have 5 volunteers, where each volunteer has 1 card in their hands. And then the magicians start by asking the question.
Hold on, Brian, I have a question.
Yeah, go ahead.
Do you cut the deck in between passing the deck around to give cards out to volunteers, or do the volunteers essentially get the top 5 cards on the deck in some order?
That's right. You cannot cut the deck in between.
Okay,
so you
thanks.
can only cut it at the beginning, and then you pass it, and then they take the top cards.
Got it. Thank you.
Yeah. And then the magician asks the question, would all of you who had a red card, please stand up and mentally think about your card. So between the 5 volunteers, those who host the red card will stand up. And then the magician can actually just name out all the 5 cards, including their rank and the suit. So a note here is that the cards are well out of the performance control. It's not tricked or marked in any ways. So the question is, how does this work? And I suggest you not to look at the book because that will not be fun. So I prepared a quick discussion here just so that we can kind of discuss how do we think this trick works. And I have 2 questions here that could help us a bit in terms of understanding or kind of have a guess of how it works. So the first question is that what information could the magician obtain based on the question and the response of the volunteer? So let's go back to the question here. So here is the question, which is that, would all of you who have a red card, please stand up and mentally think about your card. The magician knows how many cards are red. Yeah, that's true. What about the positions?
Yeah, you said that they passed them, but the magician could probably still remember what order those 5 people got the cards. So I'm thinking, is there a way to distribute the red cards so that any sequence of 5 in a row appears in a unique place in the circle that is the deck?
Yeah, I like that.
Yes, that's actually exactly what happens. This discussion goes a lot faster than expected. Thanks, DK.
I didn't know the answer. It was just a guess.
It's a very good one. Well,
But
that
I feel
ruins my timing. Just kidding, just kidding.
My combinatorial intuition says that doesn't seem like there are enough possibilities. And I'm also wondering which version of the set deck is this? Does it, how many people would you have to do in order to do this with, like, so does it work with set junior where that has 1 fewer dimensions, or yeah, anyways.
Right, yeah, we'll get to that. And yeah, like BK brought up a good point that it is cyclic. So yeah, I'll definitely repeat that. It's actually the next slide. So BK is like way ahead of us. So it is cyclic, which is why we're only cutting it, because a funny thing about cutting the card is that for a lot of magic tricks, cutting it doesn't ruin the property that you're trying to obtain. However, shuffling does, which is why we're only cutting it. Okay, so here's the key. By asking this question, the magician was able to determine the exact color patterns of the 5 cards, which means this includes how many red and also includes their position, right? So in total, there are 32 answers. And the reason for that is that, well, if you have 5 cards, and then the color of each card would be either red or black. So for each of these, there'll be 2 choices. And since each of these are independent, that'll be 2 to the power of 5, which is 32 choices. And it just happens that the deck was actually 32 cards. It's not a whole deck, but according to the book, none of the volunteers actually asked about it. So I didn't mention that either, but that's part of the trick. So the question here is that what if the deck is carefully arranged so that each consecutive set of 5 cards has a unique color pattern? Now, what does that mean? Let's say, for example, my 5 cards looks like this. So the first card is red. The third one is red as well. And then the rest of them are black. Now, what if I tell you that this pattern only appears once in the entire deck? Well, if that's the case, then if I have the magician and I memorize what these cards are, I can tell exactly what these 5 cards are. So that's essentially the idea behind the trick. Okay, now the question is, how do we arrange this deck? Well, this is actually the example provided on the book. So what magicians will be doing is that the deck will be prearranged, and then he or she are free to cut it because that doesn't ruin the property. And then let's say, for example, the 5 volunteers says that after he asks the questions, only the second volunteer stand up. Now, what does that mean? That means the second volunteer will have a red card, and the rest of them will have a black card, like this. And based on this, in the book, we actually convert it into binary, which means that black corresponds to 0, and then red corresponds to 1. So this is the sequence which exists here in the deck. And as you can see, we can know exactly the cards. There are some weaknesses to this trick. For example, the first one is that you have to have a reference sheet. Like, I cannot imagine someone actually memorizing this for the trick itself. Even if you do, it's gonna take some time for you to just find that specific position. Like, imagine you're just doing a trick in front of 200 people and it takes you like 1 minute to figure out which cards you're trying to say. That would not be very impressive. So, but yeah, this is the version layout in the book. Later on in this chapter, I think they actually mentioned some like enhancement that you could do. For example, you can have ways to get rid of the reference sheet. Yeah, so this is like
to perform this trick live, do you need to basically have these 32 options memorized?
Not if you have the reference sheet with you.
Right, sure. That's less impressive to like
yeah.
look at your notes, right?
Exactly.
Oh no. So as an amateur magician myself, you can hide this reference sheet or hints to this reference sheet in all sorts of places. So I can hide it on a card, for instance, in my hand that you never see. I can hide it on the back of the deck. And so while the people are arranging, I just casually move my hand and I can hold it out of the corner of my eye. So it's not obvious that you're looking at a reference sheet at all. And there's also, you can shorten the memorization too, some with going on here. But yeah, there's a lot of ways you can hide that you're glancing at a sheet like this.
You're going to get kicked out of the Magicians Union there, Rob.
Oh no, that's all common knowledge.
It is. A lot of tricks are done by that actually. But the good thing is that the trick that we developed does not need a reference sheet at all. Everyone here can easily do it in like 5 seconds. So let's dive into that one. Yeah, let's see. Okay, so a quick introduction to set. So this is the set we're talking about. I'm not sure if this is what BK referred to as the junior version or not, but it's the one with 81 unique cards. I actually have a copy here, thanks to Professor Ignan 80. Let me show you some deck.
That's like the regular set deck.
Yeah, it's the regular one.
Yeah.
Basically, this is the back and this is the front. Okay. All right, so the deck consists of 81 cards. Every single one of them are unique. They vary in 4 features. So it could be numbers, colors, filling, or shape. People might have different names for these features, but this is the name that I'm using. For the numbers, you could either have 3, 2, or 1. So I have an example here. So for example, this one, it has 2 shapes. So the number here will be 2. This one will be 3. And then for color, you can have purple, red, and green. So this one will be purple, this red, and this one's green. The filling, there are 3 types as well: striped, solid, and unfilled. So these are the striped one, those are the solid, and these are the unfilled. And then for shape, we have 3 shapes as well. We have diamond, oval, and squiggle, which is why we have 81 cards, because you basically have 4 features, and for each feature, you have 3 options. Where's my pen? Yeah. Which gives you 81 options. So that's where the number 81 comes from. Okay. Unfortunately, we will not talk about how to actually play the game here. but we could have a discussion later. We're not talking about it because it's not too relevant to the trick itself. We're using it just because of its.
And if you let mathematicians play set too long, we'll get sidetracked and only be doing that for the next 90 minutes.
That's very true. So yeah, we're only using set because of its very, very amazing properties. But yeah, you can always learn more. I attached a link here. I think there's tons of resources about it. I'm not the best set player, to be honest. I'm not very slow, but relatively slow compared to my friends. Okay, so I'll do a quick trick demonstration here. As I say, because we're online, this might not seem as impressive, but I'll try my best. So would one of you please pick a feature? So a feature means that you can either pick number, color, filling, or shape, and just type in the chat or just shout it out. Shape?
Andrew picks
Okay.
shape.
Let's do shape. All right, let's do shape. So I'm just gonna write a mental note here. We're gonna pick shape. Okay, someone gave me 4 shapes. Doesn't have to be the same. It has to be a squiggle, diamond, or what's the other one? Oval, yes. Okay, I have some
Diamond, diamond, squiggle, diamond.
diamond, diamond, squiggle, diamond. Okay, diamond, diamond, squiggle, diamond. All right, so now we have 4 shapes here in this particular arrangement. And what if I guarantee you that this arrangement is already embedded in this deck here? So it goes this way, so horizontally, and then vertically. So you will look at it this way. Now let's find this arrangement together. Diamond, diamond, squiggle, diamond.
5th row in the middle.
Here,
Yep.
got it. Anyone want to try again? Any other features? Number? Let's do number.
Got a 3, 2, 3, 1.
3, 2, 3, 1. All right, do we have that?
Yeah, it's split from the 2nd row to the 3rd, starting with the green shaded 3 ovals on the right-hand side.
Ooh, nice. Yeah, so thanks. As it turns out, no matter what feature you choose, no matter what arrangement you choose, it's always embedded in this deck. This is the best way I can think of to perform this trick online. But yeah, I believe the offline version is much, much clever. Okay. All right, now I'm going to talk about how this works. Hopefully that was like I don't know, impressive enough to get everyone interested in what's going on behind it. Okay, so I have to introduce something called a difference sequence. So a difference sequence is a cyclic sequence of a given alphabet with size k, for which every possible subsequence of length n in this alphabet here appears as a sequence of consecutive characters exactly once. So it's a bit of it's a bit complicated, this definition here, but I have an example here that will make it a lot easier. By the way, notation-wise, we denote a difference sequence as BKN, where the K here means the size of the alphabet, and the N means the length of the subsequence. Now, what's an alphabet here? Well, an alphabet essentially is a set with some elements with cardinality K here. So for this example, we have B33, where the first 3 denotes the number of elements in the set here. And just for convenience, we're just going to use 0, 1, 2 in our alphabet. And then the second 3 means the length of the subsequence. Now, what does that mean? Well, if you have 0, 1, 2, how many subsequence could you construct with length 3? Well, you could start by listing them out. You could have 0, 0, 0, 0, 1, 0, 0, 1, 2, and so on. But you get the idea. And as it turns out, that will be 3 to the power of 3, which will give you 27 choices. And this sequence here that I have typed out, as it turns out, this is a de Bruijn sequence of B33, because you can check that each of the 27 strings of length 3 appear once and only once as a consecutive subsequence. So for example, it contains 0, 2, 1, 2, 1, 1, and then you can just keep checking. It contains everything, which is why it has length 27, right? And also it's cyclic, means that you can go around it. So you can have 2, 2, 0, and you can have 2, 0, 2. Yeah, I hope that's clear. Now, the next question is, how do we find this sequence? Like, we cannot just program something random and then just keep finding a sequence of 27 strings. That's going to take forever. Trust me, I tried that. It takes a very long time. Depends on the size of the alphabet. So we use something called a de Bruijn graph. This is a very long definition, but I will quickly go over it. Again, we have an example that makes this much more clear. So again, that A be the alphabet with K elements. So the notation that we're going to use for de Bruijn graph will be G of Kn. So similar to B of Kn, except that B represents the actual sequence, but G here represents the graph. It's a directed graph. Basically, it means that a graph with directions with Kn to the power of n minus 1 vertices. We will explain why this is the case. A label with all possible strings of length n minus 1 from A. So all the possible combinations of length n minus 1 depends on what n is here. So for each vertex, the vertex are labeled. It's labeled this way. So this is the sequence from A1 to n minus 1. And we have a directed edge. So an edge connected a vertex to a vertex. So for example, if I have a vertex here and another vertex here, let's call this one V. And then call this one, I guess, W. So this is the second vertex. And as you can see, the label here is a bit different from this one. And the reason is that we have a directed edge from V to W labeled as D. Now, what this edge does is that it takes this sequence here, it removes the first letter or element, whatever you call it, and then it appends the label itself, which is why we get this sequence instead. So we'll just keep doing that until we've constructed every single possible directed edge. Now, let's see what that looks like. So this is an example of a G33. And the reason is that, for example, if you have like the alphabet that we have shown before, which is 0, 1, 2. Well, by definition, all the vertex here will be all the possible combinations of 0, 1, 2 with length 2. So as you can see, we have 0, 0, 0, 1, and all the other possible combinations. Now we have all the vertices. We are going to try to construct the edges. So how does that work? There are many edges here. Let's look at this one, for example. So we're going from 2, 0 to 0, 0. And the arrow is this way if it's too small for some people. Okay, so we start at 2, 0. We remove the first number and we append another 0 here to get this vertex. So that's essentially what happens. And this is how we construct all of these edges over here. And which is why they're directed only one way. And an interesting thing you see is, for example, here, I could have a loop itself because I could append a 2 to 2, 2, remove the first one, I will still get 2, 2. So this is still valid. Now, the question is, why are we doing this? Well, that would require me to introduce another definition, which some people probably already know, which is an Eulerian circuit, or we call it a cycle. It is a trial in a finite graph like this one that visits every edge exactly once and starts and ends on the same vertex. So a good example would be, let's say these are the vertex. Yes, this works, yeah. And then Eulerian circuit would be, if I start from this vertex, I could go this way, and then I'll end up at the same place while passing through all the edges. Okay, and now this is the very, very important sentence here, which is that traversing through an Eulerian circuit will give us a de Bruijn sequence. Now, how does that work? Well, we have the graph here already, and what we're gonna do now is we're gonna construct a circuit. So let's try doing this. I already have one sequence here, so let's just try going through it and make sure that it passed through everything. So it's starting at 2, 2 here. It goes to 2, 0. Oh, this is gonna get really messy, but let's try it. Let's go to 0, 2. Goes to 2, 1, 1, 1, and then it self-loop itself because it has to pass through every single edges. So this has to happen. 1, 1, and then 1, 2. Notice the arrow, you cannot go the other way. 2, 1.
I think that was the other arrow on that one, but
Yeah,
you're going to go right back anyway, right? So
yeah. And then we go right back. So that's 1, 2. 2, 0. 0, 0. And then loop itself.
0, 1. Oh, never mind, sorry.
Oh, okay. Yeah, I thought I missed something. 0, 2. 2, 0. Yeah, as you can see, the whole talk is just us going through this graph. Yeah, 1. Like, it's not necessary, but I figured why not just make sure it goes through everything. 1, 0, 0, 0. And also, of course, it cannot repeat, right? 0, 1, 1, 2, 2, 2, 2, 1, 1, 0. Okay, that looks good. 0, 1, good. We haven't done that. And then go back to 1, 0, 0, 2, 2, 2. And then I believe it goes around. So it goes back here. Exactly. It did good. Yeah.
woohoo!
Sneaky.
Yeah, we did it. I wonder how I found this in the first place. This is very tricky. But yeah, so now we found a loop here. And what we need to do is that we read off the edges. So remember how each edges are labeled. So by reading off the label, this is what we get. And guess what? This is a de Bruijn sequence of 3 and 3. So as you can see, de Bruijn sequence is not unique because you could have many different ways to construct this kind of like path. But yeah, this is kind of like a more efficient way to find a de Bruijn sequence.
Labeling the edges like that is clever, right? To
Yeah.
keep track of and make the sequence. I like that a lot.
Mhm. Okay, now I think a lot of you are asking a question like, that looks very, very complicated. do you have to memorize that for the trick? I'll keep you guessing, but I think most of you know the answer is probably no. Otherwise, I wouldn't be presenting this. But before we do that, let's give it some context. Why have I been doing B33? Well, the reason is that I need this alphabet for a set. Remember how for each feature we have 3 options? Well, that's why my alphabet has 3 options here as well. So now I can actually create a bijection between these numbers and the features in the set deck. So for each of these features here, I could assign the options to a number, right? And if I do that, I can use 4 numbers to fully describe a card, where each numbers can describe one of these features. And we're gonna do it in this order of number, color, filling, and shape, just for convention purposes. So for example, if I have the string 000, sorry, 4 zeros, I can just go back to the table. I can be like, okay, so that'll be 3. The color will be purple. It'll be striped diamond. And I know exactly what that card is. So yeah, this is just like giving it a bit of context, which we will be using very, very soon. Okay, now in order to perform this set trick, what we actually need is a B34. And the reason is that instead of having a subsequence of length 3, we need a subsequence of length 4, because again, we need 4 numbers to describe one card, right? And that happens to be 81, because 3 to the power 4 gives you 81. Now, based on this construction, every 4 consecutive digits of the sequence provides full information for one card and partial information for the 3 other cards after it. Now, what does this mean? Well, let's say I have a sequence here. Let's just give an example. Let's say 1 0 2 1 0 0 1. So this is 7 numbers, right? And these 4 numbers will tell me information about a card. Actually, let's do only 4 numbers. Right. Now these 3 numbers over here, 0 to 1, actually tell me partial information about some other cards, because this also describes the features of some other cards as well. But I'm missing a number here, right? And the same ideas to these 2, except this time I need 2 more digits, right? So this is essentially the ideas of it. Okay, let's move back here a bit. I just want to make sure this is clear. So for example, if I have a sequence of 81 digits, then that sequence will embed the full information of how I'm arranging this set deck. Does that make sense? Okay, good. So now here's the question. Do we have to memorize the entire sequence of length 81? And the good thing is that luckily, no. We have actually some very, very special different sequence that will do that for us. And they're actually recursive. So you can have a different sequence that's recursive itself. And we're going to define them this way. So if they're recursive, it gives us the ability to predict the sequence beyond a given substring. So the definition is that we're going to start off the sequence with 0001. And Bn, where n is any arbitrary number greater than 4 and less than 81, is obtained recursively using this. So Bn minus 3 plus Bn minus 4 addition in modulo 3. So what that means is that, for example, if you have 0001, the next digit here would be the sum of these two digits, which will be 0. And then you start again, will be the sum of these two digits, which would be 0 again. And then this one will be the sum of these two digits, which would be a 1. And you keep going, you keep going, keep going until you hit B81 here. And after you've done that, you will find out that if you keep doing that, you will just go back to the beginning because it's cyclic. So it is a recursive de Bruijn sequence, which is very interesting. Like, it's fascinating how these kind of constructions actually exist. So this is how we actually constructed, like we said before. This is the entire sequence just by the idea that we just showed. So starting with 0001, and then this is the entire sequence of length 81. Yeah, so in TetraCycles, this name is actually inspired by this idea here. But I will get to that.
Yeah, is it obvious that that produces one of these sequences?
Sorry?
It's not obvious to me that that produces a de Bruijn sequence.
This?
No, the recursion.
Right. I believe it's a very special constructions. Like, it doesn't always works. So a bit of the context is that for B34, there are actually many, many different sequences. I don't remember the exact numbers, but I think it's over 10 to the power of 8. And I think the unique de Bruijn sequence that are actually recursive, they're only around 6 or 7 of them. That's my memory, but I'm not entirely sure. So it's very rare, and it has something to do with, I think, actually, I'll refer to an article that I was reading before about this. But yeah, it's very rare. And yeah, it's not very convincing how this will work, right? So,
Wait.
Is it?
So it's like Merced and primes, where like it's a place to look, but it doesn't always work. Okay.
Yeah, that's true. It's,
okay.
Yeah, it just happened to work for B34. Like, this sequence here is a de Bruijn sequence. It contains every single substring of length 4, and it's recursive. Without this, the trick wouldn't be very, very useful. You would still need a reference sheet.
Mm-hmm. So, Brian, was this part of the work that you did, is that you found this sequence, or was it a thing that already existed and you've turned it into the trick?
Right. I believe the trick, the sequence itself already existed. Like,
okay.
All the recursive de Bruijn sequence are already known.
Okay.
We just turn it into a trick. Yeah.
Yeah. No, that's cool too. I just wanted to know.
Yeah. All right. So let's reveal the trick itself. So I guess some of you have already guessed how this trick will work. First of all, we'll arrange the deck in this order. So how we do that is, for example, you look at the first 4 digit. That'll be your first card, right? And then the second card would be the second digit to the 5th one. And then you just continue doing this until you have arranged all 81 cards, basically. Another thing I should mention about this sequence is that notice that how this sequence is embedding information about all 4 features, which is why we're calling it in TetraCycles. Because in the case of the trick on the book Magical Mathematics, it's only embedding information about the color, right? But in this case, because of the special property of the set, we will need a sequence that embed all 4 kinds of properties, which is why instead of in cycles, it's in TetraCycles. All right. So yeah, like I said, this will be the first card, 0010 will be the second card, and so on. Now we have the deck ready. Let's do the trick. So first of all, we cut the deck repeatedly because again, that does not affect the trick itself. So I'm just gonna take this out just for the visualization of it. So we're gonna, this is 81 cards, so it looks a bit thick. We're just gonna cut it. How do you even cut 81 cards? Oh, wow. Like this, I guess. Oh, oops. Yeah, that will happen.
Yeah.
If that happens, your whole trick is over. Just try to do it next lecture or something like that. But anyway, you hand out 4 cards to the volunteers. Now we don't need 5 volunteers, we need 4 volunteers. The magician asks, which feature would you like? Would you 4 like to describe? So similar to what I did before for the online version. Let's assume the volunteers say shape, which I think we did that for the first time. So good guess for me. All right. And then the magician asks, would all of you holding the diamond please raise your hand? So let's assume only the third person raise their hand. And then we have to ask another question, which I think it makes sense because we cannot interpret all the information just based on one question, since it has 3 features. The magician asks, would everyone with an oval please raise your hand as well? So let's assume that this time the first and fourth person raise your hand. And now we have all the information that we need to name out all 4 cards in order, including their number, colors, shadings, and shapes. So a quick visualization of what happens and how we're going to do this. So technically, you still need a reference sheet, but not the reference sheet before. This is the reference sheet that you need. It's a lot easier, and if you really want to memorize it, it's not too hard now. So this is a quick visualization of what happens. We ask who has diamonds. The third person stand up. We ask who has oval. The first and the fourth person has it. So we deduct that the one volunteer that did not raise their hand must have a card with squiggle shape because there are only 3 options. Now, we have the order that we want, which is oval, squiggle, diamond, and oval. And now we can go back to the sheet here. We say that, okay, cool, that corresponds to 1201. And since since shape is the last feature here, based on just our convention, again, it doesn't have to be, but shape is the last feature here. Instead of going forward to deduct the next 3 digits, we actually have to go backwards to deduct the 3 digits beforewards. So, which is these 3 digits. We're going to denote them as BI plus, this should be a 1, sorry about that. I plus 1 and BI plus 2. Okay, so by our recursive definition, now instead of adding, we're doing subtracting because again, we're going backwards. So quick visualization of what happened. We have, if I remember correctly, 1201. And then we need 3 digits here. Now remember this digit plus, sorry, it's not a 0. That's not what I meant. This digit here plus this digit is supposed to give you, I think, this one, right? So in order to get this one, it's an easy subtraction. 1 minus 1, that will give you 0. And then we do the same thing. 0 minus 0, that gives you 0 again. And then 2 minus 0, that gives you 2. So we have our entire sequence, which I think it's shown on this slide here. Yep, which is 2001-201. Remember that we always need 7 digits to read off everything. And now we have the entire sequence, we can actually tell exactly what the cards are. So the first card is embedded by these 4 here. The second one, we just move 1 digit forward, will be 0012, right? And then the third one will be 0120, and then 1201. And now we go back to the table again. We can match exactly the cards. So the first cards will be 2 shapes. It's purple, it's striped, and it has oval, which is this one. And then we do the same thing for the rest of them. And now you can name out all 4 cards without checking a reference sheet. Because it's recursive, you can do it in your mind. Okay, let's see. So what's next for this? We actually have an article regarding this trick that will be published on Math Horizon by MA, which will be the April issue, I think. And another thing is that I would actually love to try out this trick in person once the pandemic's over, during a large lecture. Hopefully, I don't know, a first year calculus class with like 200 people at least, just to see how it goes. Because it's hard to think about like how the audience will actually interpret this when you're like online and stuck in your home. Next is the, yeah, I would love to investigate more application of different sequence. Like BK mentioned before, it's not very obvious why this recursive different sequence actually works. And there's actually a lot of like underlying number theory stuff in it. But moreover, like it's a very neat concept. And I think it could be applied to a lot more magic tricks. Like having a sequence that each subsequence has a unique properties is like super neat. And I think we can use it to so much more magic tricks. And yeah, the last one is kind of like a thing about myself, which is that I'm currently looking for some research opportunities open to all fields of mathematics. Now, I want to give credit to many people here. So, like I said before, the trick is a variation on the in-cycles trick developed by Persi, Diaconis, and Ronald Graham. It's elaborated in their book, Magical Mathematics. If you don't have this book here, I strongly recommend it. It's a great read. Yeah, reading chapter 3 got us started on this. So we dedicate this work to the mathematical legacy of Dr. Ronald Graham. I will also I'd like to thank Professor Glenn Adey at UTM for supervising the summer research, as well as Dr. Tom Egger, who is the editor of Mathematical Association of America. He was very, very helpful in terms of reading our articles, giving very, very constructive recommendations and suggestions, and also his constant input and a beautiful Debrink graph. A fun fact is that the Debrink graph that I showed before, the planar version of it, is actually drawn by him, because my skill in terms of using LaTeX for actual graph is very minimum. I find that to be very, very tricky, being able to draw something like a very neat graph. So yeah, I really appreciate him doing that. And yeah, the work couldn't be possible without these people. So yeah, I think that concludes my talk. I'm sorry if my voice is a bit shaky. My room's kind of cold, and to be frankly, I'm a bit nervous. And yeah, I think that's everything.
Really? Brian, you did great.
Yeah,
That was
this is
fantastic.
wonderful.
Thank you very much.
Thank you.
Well done.
Awesome.
That
I'm
was
so
amazing.
impressed. I think that
Oh, hi, Parker.
you're the first undergrad that we've had give a talk at Talk Math with your friends. And
That's
so
right.
you totally rocked it. I want you to know, like, this is super cool. So
Thank you
rock
so
on.
much. That means a lot. Thank you.
Yeah, we totally need more undergrads. So
Yeah, for sure.
awesome. I'm gonna go find my set deck. It's somewhere upstairs.
One of the things I put in the chat was a digital one too. You could please play the game.
I went to see that, but the thing is, like, I wonder about like the kinds of mechanical processes about doing this thing that Brian suggested me about doing all of this cutting stuff. Like with this is not something I've ever tried to physically do. Right. And I think that just the card manipulation would require skills that I don't yet have, and it's going to involve a lot of paper cuts.
Well, and it looked like
Okay.
Brian has been practicing, because like he had a specific kind of way he was holding his deck and moving his hands. It didn't look like you were watching magician videos to try and get the tips on how to pull that off.
I think a two-handed cut with a large deck, I mean, unless you have small hands, that could be a problem. But otherwise, I think it just takes a little practice.
No, you just you
I
put
also imagine it would be easier with a table. So you just
yes.
pick up the top one, put it over,
Yeah,
pull the next
exactly.
piece up top.
Yeah, you can always just use the table. Yeah.
But
That'll
it's
be a lot
harder to do
easier.
that online to show, well, if your camera's not pointed there.
Yeah, well,
There's
then also
an-
you lot less likely to have the problem you had, Brian, where one of the bottom cards flips out of your hand. Not that I ever had that happen in public. And
There's a closely connected issue, which is if you perform a cut or a shuffle or any of these too cleanly, then people will get suspicious that you're like, you did something sneaky. Even if you didn't, whether or not you did, they can't look too clean to lots of audiences.
And it doesn't actually matter, Brian, if Brian dropped the bottom card or two, as long as they take from the top, the sequence wasn't disturbed.
That's true.
So you could like purposely toss a few. I mean, it would be annoying to rebuild at the end, but
Only on the last cut.
yeah, exactly.
Right, but I've seen lots of magic shows that definitely lean into the oafish comedy, so I could see that fitting in if you planned it well.
And silly hats, TJ, would they be wearing silly
I don't know what
hats?
you're talking about.
So a friend of mine has been teaching a sort of math for liberal arts class and has been doing some stuff with set at the beginning. And I wonder if these ideas could help understand when it's possible to get stuck. Right, this sort of list seems possible. Like that you might be able to use it to do some combinatorics about whether or not, and in particular, I think she noticed that you could never get stuck. Well, like you never get stuck with 3 cards if you're playing with a deck, it looks like. And it seems sort of connected. So.
while we're on Mathemagic tricks, I had the pleasure, I just put it in the chat. There's another one of 52 mathematical magic tricks. And one of the neat things about that one is there's a mathematical index in the back where you can look up by topic. So if you want to look for tricks involving matrices, there's 3 or 4 tricks with matrices and you can look that way. Really neat book. And I comments on Twitter actually too. So
Brian, you said this was an independent study project? Like, did you do this during a semester?
That's right. We did it last summer, I believe. So last summer.
Okay.
Yeah, that's when that happens. It was like what we call a reading course. So basically, me and Professor Parker was, I guess, like exploring different topics, and then it just sort of happens. Like the course itself is not about magic trick, but it kind of just happened that we find this applications and it's like super cool. So we kind of just write an article about it, and yeah.
I'm a co-organizer of the MOVES conference, the Mathematics of Various Entertaining Subjects, which is a recreational math conference. And this would be a neat presentation for that. You might submit to present.
Oh, that would be awesome. Do you have a link, or I could search it up?
Yeah, I'll put a link in the chat.
Okay, thanks.
It's the dates are going to be changed. It's currently scheduled for August, but it's going to be moved later.
Great. Well, let's do our little advertising before we thank Brian. So I guess I'll do it. It's a little awkward because next week is me. And I am here. So I will tell you a 30-second summary.
Wait.
Whoa,
Hey, everybody.
we can-
Next week, BK will be presenting. BK, can you share something about what your presentation will be about?
Sure. So I'm going to talk about an idea that comes from rhetoric, but has been used by math education researchers since the 80s. It's called Toolman analysis. And every time I've ever talked to a mathematician about it, they're like, oh my goodness, there are words for the things that we do. So amazing. And so it's basically about like, how do we decide if we accept a mathematical argument? And I think it's really powerful. And I read about Toolman analysis with my students who are learning about proof. And so we're going to do some of those kinds of activities. We're going to learn a little about it. And I'm going to talk a little about how I use it to help students understand what the heck it means when a mathematician asks them to write a proof. So, and then my other hat back on. Can everyone please join me one more time in thanking Brian for a really awesome talk. Thank you.
Yeah.
Brian, this is cool.
Oh, good.
Thank you
Thanks,
so
Brian.
much.
That was
Thank you.
awesome.